Hi, welcome back. This is BI 3144-6134, and I want to continue from where I left off last week. As I also announced in the class, we are going to have a live session on Wednesday rather than today on Monday. So we're talking about beam mechanics, and I had introduced beam mechanics to you last time. I'd also ended with some discussion of prior to that with energies and energy scales, and that's what we're going to discuss on Friday, along with some sums for the spring energy scales. But we're going to now go to more geometrically defined objects and discuss what are beams, bending strains, energy of beam bending, use it to understand how you can measure the mechanics of cellular properties, the simplest being the mass of an E. coli cell. It seems very simple, but you'll see with the paper it's a little more involved. It's not that easy as we would hope. And then I discuss some aspects of the energy of beam bending and the parameters called geometric moment of inertia, looping energy, and an example of all of this, the lac operon. Yes, exactly. The lac operon has mechanics involved. So now, one of the things I just want to point out is that today's series of lectures is going to be in parts. So I'm going to record one part and then record the second part and keep uploading them as they go along, which means you have to look for part 1, part 2, part 3. So as I had mentioned last time, beam mechanics arose out of linear elasticity theory from Euler and Bernoulli due to these two mathematicians and physicists. A beam is then defined as a long, slender structural member capable of carrying bending loads via deformations to its long axis, and the Eiffel Tower, the Tour Eiffel as it's called in Paris, was the first time that it was tested in the real world. The biological relevance is to cantilevers, as I mentioned in between, networks of cytoskeletal elements, as we will be discussing a little later, the hair cell of mammalian hearing, fertilization or reproduction, and how you and I are made, the sperms, eggs, birds, bees, intracellular mechanics through cytoskeletal dynamics, and DNA bending involved in epigenetics and chromosome packing, and therefore of some broad interest to biology. So let's go to it. What is a beam? So we say that in a similar convention to rods, we define the length of the beam as the longest axis. In this case, we call it the x dimension, as you see in the diagram. Now, you can argue that orthogonal to the length, there will be two dimensions. This is what you see in the right-hand side image. They have a breadth and a width. You'll see, breadth and height or thickness. You'll see very quickly that it does matter what this is. Now, in a simple case, we could imagine a square cross-section, in which case h is equal to b, in which case none of this makes sense. My point of shape makes no sense. However, a basic assumption in slender beam theory is that length is much, much longer than breadth and or width and height, or breadth and thickness. It's a very simple question for you. Do microtubules and actin qualify for beam treatment as well as DNA, actin, microtubule, DNA? And if so, is there a lower limit of length at which it does not apply to them, right? So that L is much, much greater than BH. For this, you need to go back and refer to your notes about the typical heights, lengths, and widths of these three macromolecular structures that we have discussed at length. It will hopefully also point out to you that there's a relevance to what we have done earlier and what we're doing now and what we'll do near the end. I want to emphasize that sometimes some of you may get a bit lost, and I can't really help it with this online mode. And most of you unable to show up in live sessions. I can't address everyone's questions, but if you have any, and if you're lost, you need to talk to me, right? I'm glad that some of you were brave enough to put in some very strong comments in your feedback. Talk to me if you want me to solve them, because I am not here to find out who wrote it. I am here to try and solve it, right? And I'm going to make some efforts on my part, but if I don't address your question, you need to bring it up, all right? So beams can be classified into these broad categories. This, by the way, is taken from engineering textbooks and from MIT online coursework for mechanical engineers. As a simple beam where a load is placed in the middle, the pivot point is to the left and the rolling joint is on the right. A continuous beam with multiple such flexible pivot points and multiple loads in between. A cantilever where one end is fixed, it's immobile, there's no flexibility there, and therefore all the flexure you will get is from the mechanics of the beam itself. The load is then applied to the tip. End supported cantilever is a modification of the cantilever. Combination cantilever is one where the end support is now moved a bit away from the end inwards, and a fixed cantilever or a fixed beam is where both ends are completely immobile, so the only flexing that happens is in the middle. Think of yourself holding a ruler and pressing it. Yeah, you see this bending that comes out of it. Now I know I can't show you this because my video is not turned on. Feel free to experiment a little bit on your own to gain an intuitive sense to this. Now we're not going to talk about all these. We're probably going to focus largely on cantilever-like motion, and there may be some examples of fixed beams, and I hope you will see where the relevant parts show up. So the kinds of deformations we have talked about so far with springs have been extensions and compressions, right? Stretch, elongation and reduction in length, which means that our length changes from L0 to L0 plus delta L. The strain is defined by delta L upon L0, and delta L can be positive or negative, which is what I call the extension in the case of positive and compression in the case of negative delta L, right? Since we know that F is equal to minus Ka, where K is the spring constant, then stress is related to strain as F by A is equal to E times delta L upon L0. That is, stress is related by the Young's modulus to the strain proportionately. This Young's modulus has units force per unit area, similar to stress, simply because delta L by L0 is dimensionless and unitless. Bending can have modifications, but they are neither stretching nor compression by themselves. Instead, what we see is that if we look along the length of the beam at a cross section through the beam, then we will find that we can define a so-called neutral plane or neutral axis. Above that neutral axis, elements of the beam are being stretched. Below it, they are being compressed. What about the neutral axis? Well, as the term defines it, and you can see probably and also intuit, I hope, at and along the neutral axis, deformation is neutral. In other words, there is no change. Yeah. So this is quite useful because it tells us that effectively there's a gradient of the nature of deformation across the axis that is orthogonal to the axis along which the bending is happening, and that we can get some kind of a pattern that comes out of this, or maybe you may say a law that may come out of it, and I'm going to discuss that in my next video. There's just one minor thing that it is obvious to most of you that if you take a cable or a very flexible structure or anything that you can try to bend, there may be more than just one curvatures. Yeah, you may have complex curvatures, as it is called, or complex bending. This is quite common, in fact. We have to deal with it. So for beams, at least for beam mechanics, the trick is to ignore deformations perpendicular to the axis and divide it into subsections so that you get many curvatures and then find a way to sum them over the beam. Okay. So the strategy we're going to take for deriving the strain of bending is dividing the beam into small segments. Consider an arc as a part of a circle with curvature 1 by r and calculate the energy associated with the deformation. In order to do that, we need to define a few terms. Z is the distance from the neutral axis, r is the radius of the arc, theta is the angle of the arc, and epsilon z is the strain of bending. I want to talk to you about bending strain of a beam and the energy of beam bending. So let's get to it. So again, just to remind ourselves, the geometry of a beam involves this diagram I'd shown you earlier. Along some axis where the beam is elongated, and in cross section we argue that it has along the orthogonal axes breadth or thickness and height, breadth or width and height or thickness. Yeah, we will conventionally call this height, and we will call this conventionally width. You can look up the literature and find that this is typically the nomenclature used. So in the case of deformations, as we said earlier, beam bending not the shape I was looking for, along some axis results in a lack of deformation. That axis we define then as the neutral axis, not applicable, but neutral axis. And indeed, those components below the neutral axis will undergo compression, while those above it will undergo expansion. So when the beam bends, this will be compressed as seen here, and this will expand or elongate. And by this, I'm referring to the segments, yes, sections taken for illustrative purposes, but this of course applies all through. What do we mean by expand or elongate? That means just like our spring mechanics we talked about, delta L is greater than 0 and delta L is less than 0. Yeah, negative or positive. In the context of defining the bending strain and energies, we need to define a few terms. Those are I, the area moment of inertia. I urge you to be careful about this because of this business. This is not the conventional moment of inertia that we're used to. R is the radius of curvature. Theta is the angle of bending. And we can see from classical geometry that, sorry, my beam is not looking very beam-like. Let's try to draw it again. Okay, curved beam, bent beam. This is what I mean graphically as theta, and this is what I mean by R. I'm sorry, up to here. So, indeed, I itself depends on the nature of the cross section of the beam. In other words, what we had drawn earlier as B and H, which we defined as width and height. which is effectively along the cross section of the beam. Yeah. You know this, that if you have, intuitively, if you have a ruler that is what we call a foot ruler, and maybe I can turn on my camera and show you what I'm trying to do, then there is one direction in which it is much harder to bend than in another. So let's see what I can do with my camera. All right, I think you see it. So if I have this, yeah, if I have my ruler, which I try to bend in this direction versus in this direction, you understand the difference. Now, if I call this my height, yes, cross-sectional height, and if I call this the thickness, it's a reasonable assumption to make, then if I'm bending when the H is is perpendicular to the direction of bending versus H being out of plane in another plane to the bending plane. So I'm bending in this plane, but H is in this direction, then I'm going to have an easier time bending it as opposed to this. Yes, I don't know if you see this. So if I'm trying to bend this way, it's not easy, right? And this is what is meant by the direction mattering. And this exactly is what the moment of inertia expresses. Now, we wanted to go a bit further with the beam bending energy, and we will return to the moment of inertia in a bit. So for that, we need to go back to our drawings, crude as they are, state that so let's make it a less steep bend. Okay, that's easier. This is my neutral axis. And now I can be above or below this. And indeed, I can say that the distance from the neutral axis, Z, is going to define what is going to happen to me as I bend, to the beam as I bend. Perhaps I need to move this text a bit down below, because I needed to also draw something else, which I forgot. And this is my theta, with this being R. The radius of curvature and the angle of curvatures, as we defined them earlier. So our aim is to find an expression for bending strain. That is epsilon z. Because z, remember, is going to decide because nothing changes in other words, when z is equal to 0, epsilon z is equal to 0 because it is delta L by L, and there is no deformation by definition of the neutral axis. Yeah, you agree? So we need to make some assumptions to derive the general expression for bending strain, and a few of those are the following. So let's state them. A, ignore deformations out of plane. For small elements of the beam, small beam elements, bending is likely to result in positive or negative delta L deformation. Or, right? Meaning to say, because it is above or below. Remember, when we say that, we can now go back to our previous section and say, yippee, Hooke's law applies. Yay. Okay. All right. Jumping for joy. Let us say that delta Lz, that is to say with reference to z, is equal to alpha dot z. We call this the unknown. Call this equation 1. Then L of z is equal to r plus z times theta. This is from geometry. Yeah. Because remember, if we go, let us say we go here, z is in this direction or z is in this direction. Let's assume we go up. So r plus some amount z gives us the radius, and times theta is the angle. And this is from the simple principle that for a circle, with theta as the angle and r as the radius, the relationship between the arc S and the radius is r times theta. Yeah, this is the arc length, this is the radius, and this is the angle of the arc corresponding to the arc. Defines it in fact. So for the neutral axis, what is the relation between this arc length and the angle? It is L naught resting length is equal to r times theta. So in that sense, theta is equal to L naught upon r. I wanted to call this equation 2 and this one equation 3. For any other length other than the neutral axis, what is the relationship between theta and L and R? Well, we can say that theta is equal to L as a function of z, because it changes as a function of z, upon r plus z. This is our equation. Equating equations 3 and 4, because now this is theta, this is theta, this is theta, so we can hopefully equate these. We get L naught by r is equal to Lz, because the angle is the same, remember, upon r plus z. It's obvious. This means we can simplify and we get L of z is equal to r plus z upon L naught by r. So we of course are led by this expression for L of z to the question, what is the strain, which is what we originally set out to answer, by the way, is the strain epsilon at some distance plus or minus z from the neutral axis. Assuming z is not equal to 0, meaning other than at the neutral axis itself. So then epsilon z by definition must be delta L z, deformation at a position z, upon resting length. This is our equation 6. By definition, we can say that delta LZ is equal to L of Z minus L naught. That is the meaning of change in L. So delta LZ, by substituting now with the expression we have from equation 5, can be written as L of Z, delta L of Z is equal to R plus Z times L naught upon R minus L naught. Simplifying, we end up with L naught R plus L naught is Z minus L naught R whole divided by R. These two are identical terms, they cancel out, and we are left with L naught Z upon R equal to delta L Z. This is equation 7. And now substituting 7, that is this deformation, in our original equation for how we're going to derive epsilon, that is the strain, we get epsilon Z is equal to L naught Z upon R into 1 upon L naught, which is nothing but Z upon R. Okay, and this came from purely geometric consideration. Meaning to say, we could arrive at this expression purely from geometry. When Z is the equation also allows us to see what we could have probably intuited, which is that when Z is greater than 0, positive, epsilon is also greater than 0, and when Z is less than 0, epsilon is also less than 0. And to now my second point about energy of beam bending. Right. So as we saw earlier, the strain of beam bending can be derived from curvature considerations and geometric assumptions about how we can understand the role of height from the neutral axis to arrive at an expression for strain. Now, for the energy of beam bending, we can of course go back to the microscopic view of a beam, where you see a bunch of springs, a series of springs, which are attached to the atoms or molecules that make up the material, solid in this case, with a resting length of A naught. So when the beam is deformed, the ones above the neutral axis undergo a deformation which is plus delta A, and the one below it proportionately at the same distance undergo minus delta A deformation. We ignore the Poisson's effect, meaning to say we assume that the Poisson's ratio is 1. Then the energy of the bending is related somehow to this idea that above the neutral axis epsilon Z, the strain is greater than, is positive, and the strain is negative below the neutral axis. So we end up having to write something which introduces a strain energy density term, which is W epsilon, and that can be related as 1 by 2e epsilon square, and that is our strain, and E is nothing but Young's modulus. In such a case, it is also clear that we can write the energy in terms of W, that is the energy density, times the volume, and which is because the energy density is in terms of per unit volume. And so since epsilon z is the strain change with z, we need to integrate the strain in order to get at an expression for bending energy, which is this expression here, which is telling us that the energy bending is L naught times the integral over A into E by 2R square Z square, and all of this simplifies to an expression that is a resultant of the integration, and you can find a full worked solution in Landau and Lifshitz's textbook on mechanics, the classic physics textbook. But we're not going to derive it here. And for those of you interested, please refer to Landau Lifshitz. But the working idea is that how does this EIL upon 2R square relate to what we're trying to discuss? And that's what I'm going to talk to you about next in terms of the meaning of I, that is to say the geometric moment of inertia, and the energy of looping. Thank you.